Last speaker before lunch will be Jonas Haferkamp, who will tell us about incompressibility and spectral gaps of random circuits.
Right. Thanks for the introduction. Thanks for having me. Yeah, we gave it a fancy name. You could also call it linear growth of circuit complexity, which many here might be more familiar with. Right, I'm going to talk about the circuit complexity growth in random quantum circuits and about spectral gaps of the moment operators of random circuits and how these two things are related to each other. So the first part is going to be incompressibility or growth of complexity and unitary designs in random circuits. What do I mean when I talk about quantum circuit complexity? Oh, sorry. There we go. Quantum circuit complexity and incompressibility. Well, it's sort of a folklore result that every unitary can be expressed via two local gates, even exactly. So there's always a maximum number of gates that a unitary can be decomposed into, but there's also a minimum number for every individual unitary, and this minimum number we call the circuit complexity. And of course, oh, this is unfortunate, this should be a delta. There's different things we can mean by implementation. If, for example, we approximate a unitary up to some constant error and operator norm, an operator distance, then we can call this an implementation, and these lead to different notions of circuit complexity. So we can, for example, define C delta of U to be the smallest number of two local unitaries that approximate our unitary U up to some constant error delta. And this immediately leads to a sort of very natural question, which is, does this notion of complexity grow typically in time evolution? And I'm not going to talk much about the high energy physics consequences of this conjecture, but let me just very briefly recap where this comes from. This conjecture is motivated by the wormhole growth paradox, which I don't know too much about, but in the ADS-CFT correspondence, you have this dictionary between the quantum theory on the one side and the gravitational theory on the other side. And in the gravitational theory, what happens is that the volume of black holes tends to grow at a steady rate for an exponentially long time. And if we now translate this to the quantum theory side and assume that it's some local observable, this would immediately violate one of our intuitions about quantum theory, which is that local observables should thermalize quickly. So instead, it was conjectured that the dual of volume in quantum theory is actually something more inherent to the state, for example, its circuit complexity, and that typically in models that describe the dual of a black hole interior, this circuit complexity should behave like the volume and grow for an exponentially long time until it finally saturates. So I'm going to talk more about why this is a very difficult thing to prove for the time-independent evolution of a Hamiltonian. But let's just say it's sort of a notoriously difficult problem for the same reasons that proving lower bounds on circuit complexity usually is a very difficult problem. Instead, what we can do is we can perform a tactical retreat and instead try to prove this for a toy model. And this toy model, one very common toy model for the time evolution of chaotic Hamiltonians, is random quantum circuits. What do we do here? We consider like this brickwork architecture, which is a little bit reminiscent of the trotterization of some 1D time evolution, with the big difference that instead of having the same layer of gates repeated over and over again, we draw new gates, IID, all the time. So what you do is you have this architecture, and then each and every one of these gates you draw randomly from the Haar measure on the unitary group. In a sense, it's sort of the least structured model of time evolution that still contains the concept of locality. So, and in this context, we can ask the same question: does the complexity grow at a steady rate until it finally saturates? And in particular, we can ask, is there always a much smaller decomposition into circuits? And the natural conjecture should be that this is not the case, and instead we keep growing outside of the set of circuits that we have already generated with random quantum circuits. So for me, for example, by now this problem is completely divorced from the original high energy motivation. I would just really like to know if this is the case. So you might ask, this is such a natural question. Probably people thought about this problem before, and this is definitely the case. There's a very similar model to random quantum circuits called random reversible circuits that people have been studying for many, many years. And the pseudo-random properties of these things were studied already in the 90s. So it's a little bit different in the sense that we cannot draw two local reversible circuits. So what we do is we have bits instead of qubits. And then locally, we apply permutations that permute the bit strings on these local sets of bits. But we can't permute the bit strings of two bits at the same time only, because it turns out you stay in the Clifford group then. So the complexity saturates after some polynomial time. And to actually generate arbitrary reversible circuits, you have to take random 3 local bits. Okay, I need to mention this because it's not only one of our results that we also prove things about random reversible circuits, but actually sort of a crucial step in our proof. Are there any questions about the model so far? Okay, yes? Oh, okay, so incompressible just means the circuit complexity is near maximal, or a fraction of the depth of the circuit. So the idea is that if the complexity grows linearly in time, there's no way to compress the circuit into a much smaller circuit, or at least only at most a fraction of the original circuit's depth. Yeah, this is what we call incompressibility. Okay, so how do you prove this? So luckily, a big advantage that random quantum circuits have, or random unitaries over time evolution, is in the extreme case of very deep circuits, exponentially deep circuits, we eventually approximate something like the Haar measure on the unitary group. And for the Haar measure on the unitary group or on states, I'm going to present this argument for states. It's actually very easy to prove that most unitaries are incompressible. So I assume almost everyone who has sort of a little bit of a TCS, like a computer science background, probably knows Shannon's argument for Boolean functions. So you have Boolean functions from all bit strings into 0, 1. And that amounts to 2 to the n many different Boolean functions. But if you have a gate set, a local one, the number of permutations or functions you can build with this only grows exponentially. And that means almost every Boolean function needs to have an exponentially large circuit complexity. And you can make the same argument for states. It's more or less the same thing. So let's take a small epsilon ball on all of the states. And if you have an epsilon ball in a Euclidean space, then the volume grows like the radius to the dimension. And in our case, the dimension is exponentially large, which means we have a doubly exponentially small volume. And then we can do a counting argument. We can just say, let's say we're also very similar to Shannon's argument. We have quantum circuits generated by R gates, and we draw them from, let's say, some discrete gate set. This can be made more or less continuous, but let's say we have some discrete gate set. Then we have at most G to the R many balls, right? Each of which has a very small volume. And then we can simply overcount, and by a union bound, we end up with an extremely small fraction only of the entire state space, unless R scales like 2 to the n. Any questions about this counting argument? Because it's sort of the basis of everything we do. Okay. So unfortunately, random quantum circuits are not Haar random, and it's much harder to prove the same type of concentration results. We cannot simply say it looks more or less like Euclidean space, so the volume is going to be small. Instead, it's a very structured ensemble that comes from random quantum circuits in the first place. However, they are going to form something called unitary designs. That was something that was talked about in the previous talk already. But I want to briefly explain what it actually means. In a sense, it's comes from discrete approximation of uniform measures. Not necessarily discrete, but this is where it comes from. And if you just take a look at the uniform measure on the sphere, on the circle, then averaging over it, even if you take powers of the random variable, is always 0. That's sort of clear? Good. But the problem is you get the same result, sort of a circle 1 design, if you just add up 1 and minus 1. But now if you square these numbers, it's not true anymore. Instead, if you want the same results for the square of the random variable, now you need 3 points. And it turns out that this pattern continues and you get sort of denser and denser approximations of the circle. And we can simply define more or less the same notion on the unitary group or on the state space. So unitary designs correspond to the better and better discrete approximations of this uniform measure. And technically, what we consider is is for a measure nu and some operator A, some matrix A, we consider the action psi corresponding to nu to be this thing, the t-fold twirl around u and then averaging over u. So basically, the reason this comes up very often is that every entry, basically every monomial in u and u dagger can be built by considering entries of these matrices. So let's say this equals the Haar random value, then every polynomial of degree t just gives you the same expectation values. Okay, looks complicated. What I'm trying to say is a unitary t design is simply a probability distribution on the unitary group that just matches the tth moments of the Haar measure. So up to t moments, it looks completely random. It's something like the information theoretical analog of what Fermi talked about in the previous talk. If you only have t copies, then information theoretically even this thing looks completely Haar random. And okay, I don't have equality here. I had to introduce some notion of approximation. It's not super important that you understand what exactly this means, but it sort of means if we compute expectation values, then up to relative errors even, we get the same values as the Haar measure. There are other notions of approximations that are a little bit weaker, but this is sort of the gold standard. In particular, it implies that it's even hard to distinguish from Haar up to adaptive queries. So it's really like the information theoretical analog of what Fermi talked about before. Okay, so you can define something similar for permutations where you, oh yeah.
For incompressibility, do you need this notion or do weaker additive notions?
No, for the approximate, no, for the complexity growth, we kind of need it, at least to get the very strong results.
You would get weaker incompressibility here.
You get something weaker from additive errors and trace distance, yes. You basically get that there have to be like at least a couple of high complexity unitaries. But if you want to show that with extremely high probabilities over the choices of gates, you kind of need these relative errors. At least this is how I know how to do it. And we get every notion of approximation for free from spectral gaps, which is what I talk about. So, okay, I just want to say you can do something very similar for permutations where you compare this to the uniform measure over all permutations of bit strings. And you could call it a permutation T design, but in the classical literature, the notion T-wise independent permutation is far more prevalent, even though nothing is really T-wise independent. So maybe, I don't know, maybe we can propagate permutation designs, influence classical TCS a bit. Okay, so it turns out the counting argument that I presented before can be de-randomized if you average over, if you draw randomly from a unitary design instead of a Haar random unitary. So the theorem is, and it's from this paper, oh, okay, I forgot to cite another paper by Brandao, Chemisani, Hunter, Jones, Kung, and Preskill that I cited on the previous slide, where this was really popularized and strengthened for notions of circuit complexity. But the original argument is actually already present in this paper by Brandao, Horodetsky, who observed that design properties, the design property implies strong concentration inequalities if you draw a random state psi, for example, and you consider a fixed state psi, then the probability, which you can consider to be the volume of the ball, of the delta ball around psi, of having something with large overlap is extremely small if you have a T design. In particular, this scales unless, let's say, T is already 2 to the n. This scales like 2 to the minus n times T. So it's exponentially small in n and T. And then we can do the same kind of counting argument with very small balls. There should be balls with radius. So the volume is going to be 2 to the minus n, that's what I'm trying to say. And then we can repeat the counting argument and say if you have a set of circuits generated by R gates from a gate set G, then the number R needs to be more or less like the exponent 2 to the minus nt. And this is where you get this counting lower bound on the circuit complexity from. Any questions about this? So the whole point, whole thing that I was trying to explain so far is if you have a unitary T design and you draw a unitary from it, then this unitary needs to have n times T gate complexity with high probability. And it just follows from a counting argument. It doesn't care about the notion of circuit complexity. You could also do it for any other tensor network description, or you could do it for the stabilizer rank. All of these notions can be sort of lower bounded using unitary designs via this type of counting argument. And all you need to use is that designs imply strong concentration inequalities. Okay. Yeah?
If you use the weaker notion of design, like with the diamond norm, then you get a weaker concentration.
Yeah, I don't know how to get a concentration inequality like this, because let's say I have an additive error of constant epsilon in trace distance, then I end up with a plus epsilon here. But this epsilon really should be like 2 to the minus nt to get the same effect. So yeah, I don't know how to get the same concentration inequality. I will say, just from the rank of the maximally mixed state on the symmetric subspace that you generate, you already know that there have to be a lot of elements in your unitary T design, which also implies a circuit lower bound. But I just don't know how to get this result that you have a very high probability of drawing a high complexity unitary if you draw from the gates. Okay. Okay, now how do we get unitary T designs from random quantum circuits? And the thing that we are going to use is a very old technique. We analyze the spectrum of the moment operators. So these things that I showed you before, the moment superoperators, you can sort of vectorize them. You know, they act on matrices, but you could also think of them as acting on a tensor, on a vector space of a higher dimension of 2 systems. And then it looks like this. And we don't consider the trace distance or diamond distance. Instead, we think of the Haar random superoperator as a projector onto the invariant space of the unitaries. And then it kills everything in the spectrum except the eigenvalue 1 subspace. So this thing here can be viewed as the spectral gap of this moment operator. Is this somewhat clear that what we are doing here is basically, so these two operators commute, basically because the Haar randomness always absorbs this randomness. So in particular, and this is a projector, so it has only eigenvalues 1 and 0. And the fact that these two commute, and in fact that if you multiply this with this one, you only get this operator. It means that the eigenvalue 1 subspace here is contained in the spectrum of this one. So all this difference does is it kills all the eigenvalue 1 subspaces. So this is going to be some number that upper bounds the spectrum in the ortho complement of the invariant subspace of the unitaries. Okay. The one thing that makes this interesting is you can think of this as a norm in this ortho complement of the invariant subspace, and that in particular implies that it is submultiplicative. So if you take the convolution of two probability measures, meaning you draw once from nu, and then you draw another time from nu, and then you multiply the unitaries. So it's just a multiplication of two independent unitaries drawn from nu. But if you keep repeating this, then you can amplify the spectral gap exponentially. So the only thing you have to show, in a sense, is that the spectral gap is lower bounded from zero. It's lower bounded away from zero. And then you can use this to amplify the spectral gap sufficiently to use this lemma from Brandao-Haro-Horodetsky, which basically shows that, you know, if the spectral gap or if the essential norm is small enough to overcome some exponentially large factor, then you get a good approximate design. But an exponentially large factor is maybe not an issue if you have a good spectral gap that you can exponentially suppress. And that only means you need to iterate your probability measure a linear number of times additionally. So for random quantum circuits in particular, we can think of nu as just one layer of the random quantum circuit. And then if you have 6 layers of it, this looks like nu convoluted with nu, convoluted with nu, and so on. Okay, so all we have to do is we have to prove a spectral gap for the moment operators of one layer of random quantum circuits, and then we're basically done. This sounds easy, but there's sort of a very long history of people trying precisely this. So for random reversible circuits, the first result of this kind for the spectral gap was by Gowers in 1996, who proved that it's inverse polynomial in N and T. And let me just recap that basically this means if the spectral gap is inverse polynomial in T, you have to amplify your probability measure a polynomial number of times to overcome this prefactor, right? So that he showed that in polynomial depth in N and T, random reversible circuits converge to permutation designs or T-wise independent permutations. And this was then improved over the years by Huri, Magen, Myers, and Rakoff, who got this very explicit estimate. And then more recently, Brodsky and Huri proved n to the -2 and t to the -1. And then very recently, He and O'Donnell used techniques that were initially developed for random quantum circuits to further improve the n dependence. But so far, for random reversible circuits, there's no t-independent gap known. And the problem with this is, let's say we want to overcome this factor of nt, then we get a factor of t in this. And let's say we have another factor in this of t in the spectral gap, we end up with t squared. And that means we can only prove a square root growth of complexity and not a linear growth of complexity. So we would really like to get rid of this t dependence. And then let me just say, very similarly for random quantum circuits, we have a similar history. Here it starts sort of slightly differently with a result that is not rigorous, where they considered the moment operator and interpreted it as a Hamiltonian, and then performed a mean field analysis to argue that the spectral gap should be 1 over n, up to some correction that scales like 1 over n squared, depending somehow on t. But one problem with this, I mean, I think it's a great result, which kickstarted this entire history. But one issue with this is, well, a 1 over n squared correction might be very large if it depends on t, and t scales with n. So in the regime that we care about, where t is very large, maybe this entire thing breaks down. And also, it's not a rigorous result. The first really rigorous result that contained that had an estimate on the t dependence was Brandao-Haro-Horodetsky, who proved this n to the -1, t to the -10.5. And you can see sort of this n to the -1. He and O'Donnell really used for random reversible circuits the techniques that were originally developed for random quantum circuits who got a better independence to begin with. And then so a preprint, like a paper by me, improved this like a little bit. But really didn't get very close to the classical results. And then for a slightly different model, there was a spectral gap that scaled like t inverse. But I should say every layer of this has n gates. So it's really n to the -1, t to the -1 if you compare it to the other ones. Okay, I should say I only talk about spectral gap estimates here. There have been recently other papers that improved the design dependence to linear in t, although not via spectral gaps. Okay, so here's the main result. We essentially resolved this problem for random reversible and random quantum circuits. We prove a spectral gap that scales like n to the -3, so independent of t for all t that are smaller than 2 to the n halves. And I only included this case for the quantum circuit result. For the classical circuits, we actually don't have a dependence on t in this theorem. And it turns out that using some of the previously developed techniques, we can further improve this and show that in the regime where t is smaller than 2 to the n divided by 6.1, we can go arbitrarily close to 6. The 0.1 is just sort of a choice. We actually get the n to the -1 up to logarithmic corrections in n and t. So this is really up to logarithms in n and t, we get the optimal gap in this regime where t is possibly exponentially large. Well, one corollary of this is the incompressibility of random quantum circuits, or the linear growth of the robust quantum circuit complexity for exponentially long times. So one part of the robust Brown-Susskind conjecture that we didn't answer is the saturation part. Well, okay, we know that it saturates eventually, so it is answered in some sense, but we don't have the precise scaling. We don't know that it actually grows until 4 to the n and then saturates. So far we have the linear growth until 2 to the n halves. But in this regime, the Brown-Susskind conjecture for random quantum circuits is fully resolved. And also I should say that this notion of quantum circuit complexity, it lower bounds the Nielsen complexity. So this is also solved. Okay, any questions so far? Or am I doing time-wise? Oh, yeah, there it is. Okay, good. That sounds good. Okay, no questions? So then I can tell you more about how we actually obtain the spectral gap. And I should say this part only concerns the reduction from random reversible to random quantum circuits. So please just really believe that random reversible circuits are already gapped for this part of the talk. And then I can explain to you how from reversible circuits we get random quantum circuits. Okay, it turns out I'm using the same ensemble as Fermi used in the previous talk. I'm also using the PFC ensemble, where we draw a random permutation uniformly from the set of all possible permutations, a random phase, binary phase, and a random Clifford unitary. And so we are actually directly using the result by Medgar, Poremba, Sinha, and Ewan, which proves the non-adaptive security of this ensemble. And it turns out we don't actually care about security against any ensemble. We very specifically care about this diamond norm estimate of the difference between the Haar random operator and the PFC moment operator. They show that in diamond distance, which measures the distinguishability, the one-shot distinguishability of two quantum channels, this is extremely small in the regime where t is smaller than the square root of the state space dimension. And it turns out that we can use this because what we want is we want a spectral gap estimate, right? And a spectral gap estimate, the operator norm is the induced 2 norm, so the 2 to 2 norm. And this 2 to 2 norm is upper bounded by a product of the 1 to 1 and the infinity to infinity norm, which is a theorem called Ries-Thoren. The problem now is we only have an upper bound on the 1 to 1 norm, which is the diamond norm upper bounds. But for Hermitian superoperators, Hermitian with respect to the Hilbert-Schmidt product, you can show that the 1 to 1 norm and the infinity to infinity norm are actually the same. Because they are dual, the infinity and the 1 norm to each other. So it turns out that we basically only need to use this result for an ensemble such that the moment operators become Hermitian with respect to the Hilbert-Schmidt product. And this we can do by simply modifying PFC without using this estimate. So can someone guess how to make this Hermitian? because it's eerily similar to what Fermi talked about in the previous talk. The super operator, the moment super operators corresponding to this ensemble. Yeah, you add a Clifford to the other side. It turns out the super operators are Hermitian if and only if the probability measure is symmetric under inverses. So meaning you take inverses of the unitaries that you draw, and these are distributed according to the same probability measure. And this you can do if you add another C. And because I didn't expect that we would have this discussion about P, F, and C commuting, I added another F. But in the last talk, we already explained that F and P commute, so this is the same as C, P, F, C, actually. So it turns out that we get the same spectral gap estimate on this essential norm, which gives us a lower bound on the spectral gap that scales like 1 minus T divided by the square root of the state space dimension. This suggests a very natural strategy, I think, for proving now that random quantum circuits are also gapped. And so far, this ensemble has nothing to do with random quantum circuits. It's a giant matrix that we draw from, this pseudo-random permutation, and also a giant binary phase that we draw from. Each of these contains 2 to the n many random variables. So to get this closer to something that looks like a random quantum circuit, we would like to approximate each of these components or simulate each of these components by something that looks random within these subgroups. So for example, draw the Clifford unitaries by a random quantum circuit in the Clifford group, draw the phase space by some random circuit in the phases, and draw P from the random permutations, some random reversible circuit in the permutations. We want to do this, but this immediately runs into a problem. The Clifford group is not a problem. It has small complexity anyways. And for the permutations, I told you to believe strongly that random reversible circuits are already gapped. So we can just run random reversible circuits in this component. But the phases are an abelian group, and these suck at having generator sets that are expanding or gapped. Why is that? Well, gapped generator sets usually correspond to the expansion property of the Cayley graph, meaning you want something where you apply a random generator, and with a high probability, it moves you outside of the set of things you have already generated. But for an abelian phase, let's say we have some local set, all of them commute. I add another commuting gate, you can commute it to the circuit and absorb it in one of the previous gates. So we don't really have very nicely expanding sets of generators in these phases. And what we do is we try to circumvent this completely by getting rid of F. Instead of drawing a uniformly random phase, we take a fixed Z gate, and then we conjugate it by a random permutation, which generates a phase which has a uniformly random bit string on its diagonal with the constraint that there's an equal number of pluses and minuses. And now this number T, that gives us the number of moments, corresponds to the number of queries that I can make, basically. So let's say I have access to the diagonals, but only access to T entries of the diagonal at a time. If I only have very few entries at my disposal, it will be impossible to see the difference between a uniformly random binary string and one that has the constraint that the number of T of pluses and minuses is equal. And in particular, by the birthday paradox, we again get something that scales like T smaller than the square root of the dimension. So it turns out that we can just approximate F by this conjugate permutation, and P, as I said already, we replace by a random reversible circuit. And with this together with the belief that random reversible circuits are gapped, tell us that we now have a gapped low complexity walk. Something where I draw ON layers of random brickwork circuits to approximate the Clifford unitaries. Then I run a random reversible circuit on P. I have a single Z gate, and then I have to repeat this for getting something Hermitian. So we can now show that together with the previous lemma, that this auxiliary walk has a constant spectral gap for all t smaller than 2 to the n halves. So this looks a little bit more like random quantum circuits. And in particular, it has a structure that we can now exploit using a previous result of mine. This walk that I just showed you, it looks precisely like this. We have a set of subgroups, for example, the permutation group on 3 bits, or 2 local Cliffords, or drawing from the Z, a Pauli Z or the identity. So it looks like the convolution of the uniform measure of subgroups, such that each subgroup only acts on a constant number of qubits. And this previous technique, using tools developed for frustration-free Hamiltonian called the detectability lemma and the quantum union bound, allows us to show that whenever something like this is gapped in the unitary group, then 2 local all-to-all random quantum circuits are also gapped. So it seems a little bit like magic because it tells us, well, if any nice probability measure of low complexity is gapped, then random quantum circuits are also gapped, but it actually doesn't hold in reverse, or at least I'm not aware of any such lemma. So in a sense, random quantum circuits are weirdly universal for spectral gaps. And well, how do we do this? It turns out that these convolutions show up all the time when I want to amplify spectral gaps. And in particular, in this case, we really want to amplify spectral gaps to get a constant spectral gap on the entire CPFPC thing. The problem is, I want to say if locally I have more randomness, then globally this will help me with my convergence to the designs and it will give us a bigger spectral gap. But in a convolution, we cannot say this because we don't have the right operator inequalities for the moment operators. But it turns out that precisely this thing is true if I instead have a convex combination of probability measures. There I can say if I have more randomness locally, meaning I draw from a larger group, for example, the unitary group instead of the Clifford group, then my spectral gap can only become larger. So what we do is we use these techniques of frustration-free Hamiltonians, which relate products of projectors to sums of projectors while preserving the spectral properties. We use this to argue that, well, if this thing is gapped, then the convex combination is gapped. And if I have the convex combination of these probability measures, I can replace each of them with the harm measure on a constant number of qubits. And this looks far more like random quantum circuits already. Okay, so the takeaway here should be, if you have something that looks somewhat like a random quantum circuit, and in particular you draw from some random subgroups, or you can approximate it by it, then random quantum circuits are gapped. Okay, any questions? All right. So yeah, now I have to hopefully convince you that random reversible circuits are actually gapped and generate t-wise independent distributions. And this is the second contribution of our paper. The first one being the reduction that I just showed you. In this second contribution, we show the gap of random reversible circuits by finding an efficient implementation of an expander on the alternating group. I kind of lied to you a little. I talked about the permutation group all the time, but instead we have to work with a slightly smaller group because it's called the alternating group. And it's just a group of all permutations that can be generated with an even number of transpositions. It doesn't make much of a difference. In particular, all the small moments look the same. But the problem is random reversible circuits cannot generate odd permutations. So we have to deal with this instead. So what do I mean when I say we have an expander? I mean an infinite family of subsets of this alternating group N, such that the set itself is constant size, and in particular, the size of the set is independent of N. And then I want the Cayley graph of this generator set to be an expander. So I have an example of a Cayley graph. It's not related to the permuting group at all. Cayley graph just means the graph where all the vertices are my group elements. And I have an edge between them if and only if they can be generated by some generator in my generator set. So a nice example of this is just a free group generated by A and B. So you have all the elements, as vertices, and they can be connected by an edge if and only if there's some generator A or B that connects these. Okay, so every generator set gives us a unique Cayley graph, and then you can ask, is this graph an expander? And this question, whether it's an expander or not, can be related to the spectral gap of its adjacency matrix. And the funny thing is that this is equivalent to our notion of spectral gap. So this is the only thing that you need to know, basically. Kassabov proved there exists a set of generators S such that if you draw randomly from these generators, you get a spectral gap that is independent of T. And I really want to emphasize how strong this is. The number of generators is independent of the system size, and the spectral gap is independent of the system size and T. So one problem with this is, so far it's not related to random reversible circuits at all. In particular, when I first heard of this result, I strongly suspected that these are some very weird generic permutations. And if you interpret this as permutations of bit strings, they would turn out to have extremely high circuit complexity, for example. I think that was a good guess, but it was very wrong. Instead, what we can show is if you do interpret n as if you set n to be 2 to the n and interpret p as permuting bit strings, then we can actually find a very similar set of generators that is just a modification of Kassabov to make some things work. That satisfies the same things. It has a constant size and it is spectral. It is gapped. But each of these generators can be implemented with a linear number of Toffoli, C-nots, and Pauli X gates. And this is what we use to then prove a spectral gap for random reversible circuits. I should say, here's an example of these generators. It's not quite the full generator set. It's more like closer to Kassabov's original generator set acting on a subgroup. They leave some bit strings invariant. But okay, I don't want to get into this too much. It turns out that we can leverage this result on a subgroup and then prove that there exists a generator set on the full group that is also gapped. Okay, one very last thing. How do we use this to prove a spectral gap for random reversible circuits? We can use a sort of geometric version of spectral gaps. Okay, so the Kashtan constant, the spectral gap tells us if we average over our probability measure, how much does it reduce the norm of things that are not already invariant under the unitary group? And the Kashtan constant measures how much can we perturb something that is not already invariant. So we take some representation of the unitary group of some group G, and we assume that it doesn't have any invariant vectors. And this Kashtan constant in a group G for some generator set S now measures how much can I change the norm, or how much can I change psi with some element in S over all psi. Okay, so if this constant is large, it means I can always find a generator that has a strong effect on my vectors that are not already invariant under the full permutation group. And it turns out if you have a large Kashtan constant, it does imply a bound on the spectral gap. And this bound in our previous example, where we had the convolution over uniform groups, uniformly drawing groups, it's very meaningless because there we have 2 to the n many elements. So this would give us an exponentially small gap. But because Kassabov's result is so strong and only has a constant number of generators, we can use this to imply a spectral gap for random reversible circuits. Okay, so just to summarize, we can basically prove the linear growth part of the robust Brown-Susskind conjecture. There are some questions open for the very large T regime. And sort of while doing this, we kind of resolved the classical conjecture by Timothy Gowers in 1996. And we proved the spectral gap for random quantum circuits, which was also conjectured since 2009. I should mention here, there's a sort of, for the random reversible circuits, there is a concurrent work by Greta Hay and Pelikanos, which doesn't prove spectral gaps, but they prove via log-Sobolev inequalities also that you can generate T-wise independent permutations in a depth linear in T. So in a sense, they also resolve this conjecture for random reversible circuits. Okay, so, and one of the consequences, I mentioned earlier that the paper by Medgar, Poremba, Sin, and Ewan also implies unitary designs, approximate unitary designs in a depth linear in T. And there's a second paper. I should have the authors here, I apologize, by many here at Stanford, who also achieved the same result, and both of them generate approximate unitary designs in a depth linear in T, however, so far only for additive errors. And we have the only multiplicative error unitary design construction with optimal T dependence. All right, so there are some open problems. The first one I already mentioned, it's show this for all T, and in particular get the late time regime right. And the last one, which might be very difficult, unfortunately, is there any interesting result about Hamiltonian evolutions? Okay, I think I will stop here.
Plenty of time for questions.
So you have this result for the computational complexity or circuit complexity. Maybe this is a wild question, but does it say anything about the, let's say, the homograph complexity of, let's say if I want to think about this random unitaries generated by a circuit, I want to find a minimum description length in terms of qubits that feed into a quantum Turing machine. I guess the counting argument would sort of universal enough to say something there, but maybe, yeah, do you have any comments?
So, okay, homograph complexity, it's about the smallest program, right?
Right.
Your unitary. And I guess there are just not so many programs of a certain size, so it will imply some bound on the homograph complexity, but I don't know which.
Okay.
All right.
Well, I'm a complete outsider at this, but this it seems like this Kassabov set of generators must be good for other things. What are there other applications that?
Well, there's a bunch of okay. So you can also use it to generate k-wise independent distributions directly. So these permutation T designs. You can also just take Kassabov's expander and use it to generate. You don't need to use random reversible circuits. So for generating information theoretically secure pseudo-random permutations, it's really good. Then another thing that follows is there's this notion of quantum expanders, which is not exactly the same thing as this. It's like the T equals 1 case. And there are some questions related to whether there is a constant depth quantum expander. And we can also use this to show the existence of a constant depth quantum expander, for example. So in this field, you know, where you try to prove expansion properties, it's a very powerful result. I don't know of practical applications, except for generating k-wise independent permutations. I think that's used in classical computer science.
So the model of random reversible circuits you're looking at is 3 local, but not geometrically local. Is that correct? Do you have anything to say about geometric locality?
Yeah, so all these things are sort of equivalent. If you don't care about inverse polynomial factors in n, I can relate all of these models to each other. Like take any architecture, either then draw the positions at random or fix the positions and only draw the permutations locally at random. All of these are gapped.
In particular, the T independence is still holds.
Doesn't suffer, yes. Yeah. So you can also arrange your random reversible circuits in a brickwork architecture, for example. It wouldn't change this. Yeah.
Thanks.
Fantastic. What are your personal, like, what's your level of optimism about open problem bullet one? You think it's on, you would be very surprised if
I would be very surprised if someone proves it. So one problem with this, okay, so an immediate problem is all of the techniques I presented here will fail immediately because counting lower bounds also tell you that a random ensemble of Hamiltonians cannot form a very high T design because there are just not enough Hamiltonians. To form these T designs, I have to keep infusing randomness into the circuit all the time. I should say for time-dependent Hamiltonians, there's ways to relate this to random quantum circuits and show. So for some Brownian version of time evolution, this can be done. Yeah, so the time-independent Hamiltonian, there's actually a reason to believe that it's very hard. In particular, even showing that after some super polynomially long evolution time, there exists a Hamiltonian such that the circuit complexity is not polynomial. You know, show a super polynomial circuit complexity lower bound after an exponentially long time even will probably require separating complexity. Because exponential time evolution of Hamiltonians is p-space complete, I think. And you would have to show that there are not in the class of quantum circuits that can be generated with polynomial advice. So you have to sort of show p-space is not in BQP/poly. I think it's very unlikely.
You think the original Brown-Susskind conjecture is true then? Like I stated up before. And
some version of it, yeah. What number? I mean, okay. I'm not sure that it's really linear, but I do expect that it grows at some rate for a long time before. Yeah. So I definitely believe that p-space is not in BQP/poly, for example, and then the exact rate I would just expect.
Oh, I didn't like the cutoff. That's like both one.
Oh, I don't think they conjecture a specific cutoff point. This is just for random quantum circuits because what we expect is eventually you just fill the full unitary group, and this is when it saturates. For
the end, it's literally just the number.
yeah, that's all there is. It's just a just the maximal circuit complexity you can possibly reach, and we believe then it just saturates. At least with high probability, yeah. It could be that you have a linear growth for a long time, and then it sort of, it grows at a slower rate for a while. Yeah. I don't know. We think maybe it depends. Yeah, maybe it depends on the robustness parameter delta that you can pick. And if you have a large delta, then sort of doesn't grow as, you don't have a very sharp transition, maybe. Yeah. But I actually don't know. I think if we can prove a spectral gap for all T, it's pretty much sharp. I mean, at least the scaling is, at the scaling of 4 to the n, you saturate.
For time-independent Hamiltonians, do you think it might be possible to show something for shorter time scales, that it grows linearly initially and then slows down?
Yeah, so I think at least until you reach a time where T scales like n, I actually don't know if results like this exist, but it feels to me like in that regime, you would just expect entanglement to grow at a linear rate, and entanglement lower bound circuit complexity. Because to generate large entanglement, you need a lot of gates along any bipartite cut. Yeah, so I would expect at least until T scaling like n, you see something like this. At least what we can prove.
Good. If there are no further questions, then I guess we'll break for lunch, and the next talk starts at 2 p.m. But let's thank Jonas again.
I think in the PSY, right? Like right? Like